much. So hello everyone, thanks for the introduction. I will be talking today about some more advanced techniques for doing data analysis using Python. So I will just share my screen like so. But just to start with, I'll just give a brief couple of slides about what I mean by data analysis and why it's important. So in this is only a short series of slides. I will talk about some Python packages that we're going to be using. They'll be in the script that you've all seen in this email as well before the course started, but I'll briefly list them here. I'll talk about some examples of when we would use these techniques. This is not an all-inclusive list. It's just a small list of examples. There are plenty more environments where you want to use this sort of these sorts of analysis techniques. A little bit of background. Unfortunately, there's a little bit of mathematics involved in this sort of analysis. I'll try not to go into too much detail for the mathematics, but there will be some references if you wish to look up some things in your own time, but I'll try and give enough of an introduction that it makes sense. And then I have a big list of references. And so I can make sure that these slides get emailed out if you wish to have a complete list of the references here. So just as I mentioned, the Python packages, you'll probably have already seen NumPy in the previous lessons by Ashwati, as well as you might have seen SciPy, Matplotlib for plotting, and pandas. So NumPy, if you missed the previous lessons, so NumPy is a simple package that we normally use in everything we do. It allows us to make arrays of numbers, matrices, have functions that allow us to do some data analysis and manipulation of data. SciPy is a more scientific package. It has a lot of mathematical algorithms for doing more complicated equations, things such as integration, optimizing your routines, statistics, analysis, and so on. Matplotlib is used for plotting, making pictures, making figures, so we can do line plots, scatter plots, bar charts, histograms, pie charts, all sorts of things you'll have seen if you've used MATLAB before or if you've used Excel. You can make all the same figures. PyAstronomy has a lot of astronomy-related tools usually used for people who are looking at stars or planets through telescopes, but it has a lot of useful features that we can make use of, one of which I'll be talking about in the class today. And then pandas, which today we won't make any use of pandas, but next week in the next lesson we will have some pandas usage. But it allows us to load in tables of data, so things that you get from Excel and so on, and lets us reshape the data, move it around, and manipulate it in a lot of convenient ways. An example of what I mean when I say data analysis, just in case, is we have some data in some case, such as the in this case, it's the output or the you could say the profit generated by a business, and you can analyze this data and extrapolate it sometime into the future. So you can say, well, based on the previous trend, we can estimate what's going to happen in the future. This is probably one of the more common uses you'll find outside of universities. People in all sorts of business environments will do this all the time. They'll try and predict something with data that they have to guess what will happen in the future. Another type of data analysis is what I personally do a lot of, is you have some measurement that you've made in a lab or somewhere. You have a collection of data. In that case, it's those blue dots, the green triangles, and the red crosses here are some measurement that we've made. This is data I've actually taken from my PhD, but what the data is not super important. And we can add these blue curves here, the blue curve, the green curve, and the red curve, using analysis techniques to try and understand the data better. So this is the sort of type of analysis I'll be focusing on today, with a little bit of this, a lot of this. And then finally, I'll introduce it briefly at the end of today, but it will be more of a focus for next week, is working with images. So some kind of picture, maybe from a camera or generated in some type of way. It doesn't matter what sort of picture it is, but how we can get useful information from the image. So this is, again, a picture that it's a photo that I took on a camera during my PhD, and it's actually what I used to make this picture on the left here. So this is something I will show next week on how to do that. Very simple things. I won't spend too long on this because it's mathematical details, but I suggest if these are things you're not familiar with, you can ask me during this lesson, or it's something you can look up at another time. But of course, analyzing data relies on a lot of mathematics and statistics. And so we'll use a lot of terms such as the mean or the variance, standard deviation. These are things that are important to understand. So just as a brief summary, just in case these are things you haven't come across before. So the mean, by that, I'll be referring to what is commonly called the arithmetic mean. Is just if you have a collection of numbers, it's just the sum of all of those numbers. You add them all together and divide it by how many you have, and that gives you the mean. We can often call this the average as well. This is important for analyzing data because quite often the mean can tell you something useful about the data you have. Standard deviation is another thing that we'll talk about. This tells you how much variation or the spread of data that you have. So you have a big collection of some statistics such as people's height, how tall people are. You have some mean height, an average height of people, and a standard deviation is how much, what's the spread of people's heights. How far away from the average height can people be? This is a complicated mathematical formula. Don't worry too much about it. It's just in case it's familiar. Then we also have the variance. The variance is just the expected value or the mean value of the squared deviation from the mean of a random sample. It's just so it's related to the standard deviation here. But these are all things that will come up in the analysis. For now, don't worry too much if they're not something that you've come across. The next thing is there'll be some common mathematical functions that you'll see a lot of. I think I'll cover most of these today. The first one, simplest one, being a straight line. It's just given by some expression here. We use it to describe things that change in some linear fashion. So you have the slope of a line, or the gradient, given by the m, the x value, which is along the horizontal part of the axis here, and some offset value. I haven't got a picture showing this, unfortunately, but you'll see it very soon. The next is the exponential curve. So this describes things that grow or shrink at some constant rate. So these come up when you're talking about populations of people. So how the population of a city, for example, grows, that has an exponential growth rate, or shrinks at some constant rate. Or radioactive decay is another example. So how does a radioactive sample decay over time? And the exponential looks like this. It's just something that gets bigger with time, faster with time. Another common one is the normal distribution, also called the Gaussian function. It's this sort of peak here, this red peak. It describes things that are randomly chosen from some sample. So whenever you're dealing with statistics, it's probably what you'll see in a lot of your analysis. It's if you have some sample, such as say a big group of people, and you're randomly choosing from this group of people and asking them, say, their height, what you'll most likely find is that their heights will be distributed something like this Gaussian function, with most people being at one value, and then the number of people being taller or shorter will decrease in some way that follows this Gaussian curve. This is an incredibly common distribution. You'll often find it with, like I said, with any type of sample, if you're sampling from randomly from some distribution. So if you take some dice, you're rolling your dice and you're adding up the total number that you roll, it'll also follow the same distribution. If we want to think about something that's more similar to my area of work, such as in physics, you have a laser beam. The shape of the laser beam also follows the same shape. And there's many, many more examples of this as well. Then another one that I'll just introduce now is the sine and the cosine functions, or trigonometry functions. They've got some funny looking expressions. Don't worry too much about that. But the main thing is they're periodic. So they oscillate up and down, usually in time or along some distance. And this is used maybe not so much in areas outside of science. But you'll see it if you're talking about a pendulum. So you have a weight on a string swinging back and forward. You can describe how far the pendulum is swinging by a sine curve like this. The electricity that comes out of the walls of your house is also described by this. The AC current, as it's called. Light, the way that light travels, is also described by this. So it's probably more likely to be seen in a scientific environment, but it's something that I will show you about today. Another thing that I will talk about a little bit is filtering data to make it more usable. What I mean by filtering is removing parts of the data that are unwanted. It's usually noisy, as in, see this picture on the bottom right here. You see there's lots of up and down variation, fast oscillations of the data. That's often difficult for us to work with, so we want to remove that. Some simple ways to do that are using what's called a filter. So the most common filters would be a low pass or a high pass filter. And that just is what's shown on the top here. It filters out different frequency components. I'll show you a bit more about what this means in the coming lesson. These are the most common types. You'll probably see bandpass filters or band stop filters as well. These are the ones maybe not quite so common. If you've done any work, or you're interested in music, or you're interested in electronics, you'll have probably heard of these before, as again, in music, high pass and low pass filters are used quite often. Same with electronics as well for sending signals. And the last thing I'll talk about today, which is probably the more complicated thing, is a thing called the fast Fourier transform. Now, this is something I'm including just as another example of filtering data, but it's probably one of the more complicated things I'll be talking about. And it's a way of converting some signal from, I say, a time series. So audio is a good example. You have a recording of someone playing the piano. You can turn that into a set of data which shows the frequencies present in the data. So for audio, that'll give you the audio frequency, or the notes of the music. But you can do it for many more things as well than just audio. It's a very useful tool. And I have a list of references here, but don't worry about those now. One of the useful ones here I have found is there's this PDF. So I will send these slides around to you, so don't worry too much. But this PDF here is it's a book about Python for data analysis, and it's quite a useful reference. It has a lot of great information and will cover a lot of the stuff that I'm talking about today. So with that, I will move on to what to this Google Sheet here. So this is something I believe you should have all received in the email. If you haven't got the email with that, please let me know. We can paste it into the chat if you need it. It's a Google Drive folder that also has some data that we'll be using today. So the important thing to do first, if you're working alongside, is just to make sure you mount this Google Drive. You have to then give it permission, and then it'll allow you to use all of the data that's in the folder. So what I'll do first is I will go do a little bit of a recap of what Matplotlib is, because it's very important for what we're doing today. I know there was a bit of it in last week's lesson with Ashwati, where she talked a bit about visualizing data, but I'll go through it again just in case. So Matplotlib is a plotting library that allows you to visualize your data, and it's very, very similar to MATLAB. So if you've ever used MATLAB before, this will feel familiar. And the way that we want to import that is like this line here. So we import matplotlib.pyplot, and you can import it as anything you like. I just import it as PLT because that's easy to type. And this allows us to visualize some data. And so as an example, we have some array here of numbers, 1 to 5 as the x-axis or the horizontal axis, the y as some numbers from 2 to 10 is the vertical axis, and then we can just plot it by calling, in this case, plt.plot of x, y. And what that does is it plots the x values, so we can see here from 1 to 5, against y. Zoom in a little. Yes, certainly. Let me just do that. Yeah, my screen resolution is probably quite high. Hopefully, this might be a bit much. Hopefully is this a bit better? Let me know if it's still not enough and I can zoom in further. Yeah, so here we have the x plotted along the horizontal and the y on the vertical, so we get a nice straight line. So this is the simplest usage of this. The key thing to remember is that your data, so x and y here, must be the same length. So if I just do something like this, which just lets you print the length of data. Oops, sorry, that was not a mistake. That should be a code box like so. You can see that they both have the same length of 5. If they don't have the same length, you'll get an error when you try and plot it of the data must have the same shape. So just keep that in mind. It must have the same length. You can do all sorts of styling of your data if you want. You can plot it in different colors. I have a lot of lines of code here. The main thing they're doing is just plotting 2 sets of data here, which is the y data and the z data, in different colors. So the z data is just some other numbers. And we can change the style of the plot using arguments such as color. It lets you change the color. There's a big, if you look on the Python documentation or the Matplotlib documentation on the internet, you can find the list of all the available colors. it's sometimes a little bit hard to remember all of them. So in this case, I've used M, which just means magenta, which is this kind of pink color, or you can type in the name of the color blue. In this case, K is black. But there's a huge list of colors. You can also use hexadecimal codes if you really want to give exact colors, but I don't do that very often. The next thing is the marker style. So that's the marker of the points. So you can see here I've said O for the marker, which is giving it circles. V gives it these upside down triangles. X gives crosses. You can give the other way around, up the right way up triangles, and so on, which is very important if you're trying to distinguish your different sets of data from one another. Very important to use different colors, different styles. The next thing you can do is change whether or not there's a line joining the data. So that's this line style. So if I don't give it a line style, it just joins it with a solid line. If I tell it none, there's no line. You can do dashed, you can do dotted. Again, the matplotlib documentation, if you just Google search matplotlib, will have all of this information for you. You can also then label your data. So normally when we're making a plot, we want to have clear labels that describe what we're looking at. In this case, we've just said X values. I could make this, you could name this anything you wanted, and then the Y label is, in this case, data. So yeah, you can again make that anything you like, but label it something that describes what is on the axis. We can also then title our plots if we want to, just as another way to title it. So this is probably up to this point here, this will let you do almost anything you'll need to do using matplotlib. Is if you know how to label the axes of the graph, you know how to change the color of your data, change the points, give it a title, and one thing I didn't mention yet is give it a legend here. It's just the legend will label the different plots so that you can know which one is which. So here the purple data or the pink data is Y data, and the blue is Z, and I haven't labeled the black curve. But this is almost everything you'll ever need when doing this. There's plenty more functionality for making a plot, but that's something that I think takes a bit of time to learn, so I won't cover it. The other good thing we can do, which is useful for a bit later on today, and also for the upcoming lessons, is to display images. So the first thing, there's this Python package PIL. That is a Python image library. It has some useful tools for loading in images. And we can use it to load in this image, which I've called my image. This is included in the Google Drive folder. So if you have access to that, you'll see it. And this is a picture that I have taken of my cat. And so you can see we've got a nice picture of my cat's face. And you can do this with any picture you like. If it's in a JPEG or a PNG, you can load these in very, very easily. So for now, that's what I'll leave that for the kind of recap and the introduction for matplotlib. But we'll be using it for the rest of the lesson. So if I do something that I haven't explained here, and you want to know what I've done, please just let me know. So now we'll move on to data fitting. So this is where you have, like I mentioned in the introduction, you have some data, a collection of information, and I want to fit the data with something that explains how the data behaves. So the simplest example is a straight line. So like I mentioned, you have this y, which is the answer, the result is some number m times x, which is the horizontal axis of our data, plus something called c, which is just a constant number that just is some kind of offset. This m is the slope or the gradient of the line. So it tells you how rapidly, as we go along the horizontal axis, how rapidly does the data increase. And the c, like I mentioned, is some offset from 0. It's also called the y-intercept. So where, if you draw the line all the way back to x equals 0, where does it cross over the vertical axis? And NumPy has some functions that will fit straight lines for you very easily. One of them is this called polyfit, which fits any type of polynomial function. If you're unfamiliar with polynomials, there's a Wikipedia link there that you can have a look at. Whereas a straight line is a polynomial of degree 1. So it's just the simple case of a polynomial. There's also a SciPy function called linregress, which is for linear regression. That's just a way in which the function finds the best fit. It's through a process called linear regression. There are many different ways of fitting data, so I'm not going to cover every single possible way, but they all give pretty much the same result. So as an example, I would just generate some data to show you. So x in this case just is some number that goes from 0 to 50. And I am creating some fake data by making some data in a straight line using this polyval function that just creates a polynomial, and adding some random numbers to it just to make it a bit noisier so that it looks like real data. So that gives something like this. So you can see it sort of looks like a straight line, but it's got some randomness to the data, which is what we would expect in a real situation. So if someone handed me this data and said, I want to know what describes this data, can you find that out for me? One way that I could do that is to use this polyfit function, like I mentioned. And what it requires as input is the x values, the y values, and the degree or the order of the polynomial. I haven't talked about what that means, but for a straight line, degree is 1. So you can just put that in as 1 and run that, and it will now return the values of the polyfit function to p, which we can then use to generate this red straight line that fits the data. So that means that Python kind of understands how the data changes with x. And so from this, if we wanted to, we could make some predictions. So we could guess what happens at x equals 100. And so we could now predict what's happening in the future. We can check if the fitting makes sense by eye, because it goes through all of the data, so that makes it looks like a good fit. The other thing we can do is look at what has been returned from this polyfit function into this p variable here. And so here it's given us an array of 2 numbers. The first number is the gradient or the slope of the line, this m from earlier, and the second number is the y-intercept or the offset. So we can check that ourselves. So the first thing we can look at is, does this gradient make sense? Well, as we know, the gradient is how much the data increases in height compared to how far along we go, or rise over run, as it's sometimes called. So we know that the data goes from maybe approximately 50 to approximately 300. So that's 250. And then we can divide that by how far along we go, which is from 0 to 50, and see what that is, and it gives us 5. And so 5 and 4.97, they are very much the same number. So in that case, the gradient that polyfit has returned makes sense. The next one's much easier to confirm, which is this y-intercept, is where does this line cross over the y or the vertical axis. So if we trace this line back, it passes through about here. It's a little bit hard to say what that is, but it's probably something that's between maybe 50 and 25, and that's about 36. So these numbers make sense. I would say in this case, you can always trust, if the fit looks good, you can always trust the numbers that come out of this. This is just an exercise to show that it is in fact doing what we think. We can also use this other function I mentioned called linregress, which is from the SciPy package. This has a little bit more advanced functionality in terms of what it can give you. But it's much easier for us to use because we just say SciPy linregress, we just give it X, we give it Y, and it gives us a result. Now this result gives us many more parameters. The slope, which is the gradient of the line, you see that this here agrees very nicely with the number from the NumPy. The intercept is 36.4. That again agrees very nicely with what came from NumPy. But it's given us these other values here: the R value, the P value, the standard error, and the standard error of the intercept. So these become very useful when you want to start looking at the errors or the quality of your fitting, which I will talk about a little bit later on. But the main thing I wanted to show is that for fitting a straight line like this, it's very simple. You can just use the linregress function, or you can use the polyfit function, and you'll get very nice results. There's not much more to fitting straight lines, so what I'd like to do now is talk a little bit about the error in the fit, as in the fit is not perfect as we would expect because the data isn't a perfectly straight line. So one way to tell how good our data fitting is a number called the coefficient of determination, is its very formal name. You'll sometimes hear it called the R value or the R squared value. And that number goes from somewhere between, I'll just change this to from 0 to 1, whereas closer to 1 means it's a better fit to the data, closer to 0 means it's a worse fit for the data. This number comes automatically from this linregress, as I've shown you here. This R value here comes automatically from the linregress. If you want to find it from polyfit, it's more complicated. I won't be going through that because it takes too much time. So just as, again, an example, I bring back some data just like before, and we can fit the data just like before, and we've got the R value here as 0.98. So that 0.98, as I mentioned, is very close to 1. 1 means it's a very good fit. Sorry, I see we've got a hand raised. Yes. So if I see, if you've raised your hand, you can ask a question if you'd like.
Maybe he raised her hand by mistake. I don't know.
Okay. Yeah, but please feel, if you do have a question, please feel free to ask it. Okay, so yeah, this is very close to 1. So that indicates that it should be a good fit or a good description of the data. But something to be aware of is that it doesn't always, just because it can be close to 1, doesn't always mean it's a good fit to your data. So as an example, I've created some data here that is not a straight line. It's very obviously not a straight line. It's a curve. That's something like x to the power of 3. But we can still fit this with it. We can still try and fit this with a straight line using the exact same linregress function. If we try and fit this with a straight line, you see it's a terrible fit. It only describes maybe 2, 3 data points correctly. All the rest of the data does not fall on the line. But if we look at the R value here, it's 0.91. 0.91, you may think that's not very far away from 1, so maybe it's a good fit. But you can tell by eye that this is a very, very, very bad fit. That this function is not, this data is not at all described by a straight line. So in that case, you can look at the p-value as another indicator. I haven't got any notes on the p-value, but that's kind of, again, a number that if it's kind of smaller, it tells you the likelihood that the data has ended up this way by accident. The smaller the number, the better. Again, doesn't tell us much about this case. So the best thing to do in these sorts of cases here is try and see if there's something better that fits your data that gives a much better, that looks like it's much better. So a lot of the time, your fitting will rely a little bit on your own eyes. You'll have to look at what you've got and see, does this look like it's a good fit? There are mathematical tools, but sometimes you have to be a little bit careful that you don't interpret them incorrectly. So, like I mentioned, this is clearly not a straight line. So what I can do is create different curves to try and fit the data with, and see if any of them fit better. And so, like I mentioned, polyfit allows the creation of polynomial functions. So that's something like the okay. Sorry, what do you mean by not written for you properly? Not visible for you properly? Is it something with my screen sharing that's incorrect?
Maybe he says the text is not legible.
Okay, I can try zooming in further if that's easier to see. Thank you. Yeah, so the polyfit gives you different polynomials, and by polynomial, it's something that is usually x or x squared, x to the power of 3, and so on. And so you can use this polyfit function like this, just as we did before, with x and y and 1 to get a straight line fit. But by changing this parameter here, which is the order of the polynomial, to 2 and to 3, it'll allow it to fit with either an x squared, which would be kind of a, as you may have heard of, a parabola function, or an x cubed, which is kind of a bit more of a curve. And we can see if either any of these fit. And so here we see the straight line. The red is the same as before, doesn't fit correctly, but we can now fit the curve using different orders of polynomials. And from this, see that the pink curve here, which is a third degree polynomial, or the power of 3, fits very nicely. So this just tells us that the function here should, and much by eye, we can see that it should be described by an x to the power of 3. If we wanted to, what we can look at is you can look at the fitting, the parameters of the fit. It gives us some numbers here. Now these are the, maybe I'll just type it into the text here. If we have some function that looks like x to the power of 3, or a times x to the power of 3, plus b times x to the power of 2, plus c times x, plus d, like this. It's this is what it means to be a third order polynomial. And so here it's giving us numbers for a, 1.6, b as 0.38, c as 4.8, and d as 192. So now these parameters tell us everything we need about this function, and so that's how we can fit it nicely. We can actually go up and see where I created this data, and you can see that the data I've created here is 1.6 times x cubed plus 0.5, and then it's plus 400 times some random number. And these numbers here are very, very similar. Well, the 1.6, the 0.5, and this here as being 192, they're very close to what I generated on the randomness. So that means that we can say that it has fit quite well. One thing again, though, just as a cautionary comment, if you look at this data, if we had a smaller section of the data, it might be hard to see, so I apologize for that. But you see the green curve reasonably well describes what's happening over most of the range, but only once we get closer to 0, you can see it starts to move away from the data again. So it can be sometimes a bit difficult in choosing which is the correct function to fit your data. And so quite often you'll want to try and see what happens as you move away from the edges of your data. So in this case, going further to the left or further to the right, and see how the function behaves and see if you can kind of get more data to fit it. Just to make sure you're using the right function. So what I'd like to do now is move on to something a little bit more complicated than just than the polyval and polyfits. And so that's what I'm calling here fitting of non-linear functions. Non-linear, I just mean things that aren't straight lines, really. And this can be done very nicely with using SciPy. Again, they have a thing called the curve fitting toolbox. You can find all of the documentation on that at this link that I've given here from the library called Optimize. And so that just has a large collection of functions that we can use to minimize data or fit data. And I'd recommend checking this out if you want to look at what it can do. So this uses the SciPy curve fit uses a method called a nonlinear least squares method to fit data. It basically just tries to minimize the distance between the data and a function that it thinks is the right answer. So it just does a kind of a clever way of guessing what it thinks the answer should be, checking how does it compare with the data, and then making a correction, going back and checking again, and just doing that some large number of times until eventually it thinks it's found the right answer. The way that we use it is it takes in quite a large number of arguments. So this code here in the black here is an example of what we need to pass the arguments. It looks kind of complicated, but most of these things are things that you don't need to worry about. If you can give it any type of function you like to fit. I'll show you some examples of how you can write this, but this can be any function at all. You have complete freedom to make this whatever shape you like. The x data and the y data, so just like with the straight line, you have your x and your y. This thing called p0, which is an initial guess. So you think, I think this is what the function should look like. You give it some parameters. You have this sigma, which are uncertainties in your data. So often if you make a real life measurement, our data will have some uncertainty based on how accurate we think we are measuring it. There are bounds, which lets you choose how much it's allowed to change parameters. These are all things that can get quite complex. So if you are interested, I recommend checking out the details up there. And there are many more arguments that even some of them I've never used in my life, so I don't know how they work. But as a simple example, let's just have a look at a very simple example. So from this, like I mentioned, it's part of the SciPy Optimize toolbox. So when we want to import it, use scipy.optimize, and you can import it as anything you like that makes it convenient for use. I import it as SPO. It makes it convenient to just type SPO. here, again, I'm going to create some fake data just to give you an example. And I want to create something that's in the shape of a sine wave. So this is the periodic sine wave I showed you in the PowerPoint at the start. Now, I don't know if you've had an introduction to how functions are written in Python, but this is the simple way that you write a function. So if you want to write a function, you have to use def to define a function. You give it a function name. I'm going to call it my function. And then in the round brackets, you give it your parameters, or your arguments to the function. So it can be A and B and C, for example. Use the colon here to indicate that that's the end. And then you go down. And because it's Python, anything that's indented in is now part of this function. And so I can make this function do anything I want now. So I could say y is a plus b, and z is, say, a plus c. And then it can return something that's y and z, like this. Now, this will just take in 3 numbers and add a and b together, add a and c together, and then give me both of those numbers back. So I can then just say my function, well, this is result equals my function of 1, 2, and 3, like this. And it's now got some result, which I can now print. And it's 3 and 4. So this is just added 1 and 2, which is 3, and then 1 and 3, which is 4. And you can make this function as simple or as complicated as you like. But that's just as a note, if you ever want to create a function, this is how you do it. The reason you'd want to do this is because now anytime I need to do whatever's inside this function here, I can just call my function without having to rewrite all of this code again and again and again. So that's what I have here. I've made this function called sine curve, and I've given it 4 arguments: t, which is just like x. It means time, usually, in this. A, which is the amplitude or the height of the curve. W, which is the frequency of the curve. How rapidly does it oscillate? And phi, which is just it's like an offset. It's a phase, or it's called a phase, but it's an offset of the curve. So if you have a sine curve, you can shift it left and right by this phi. And so I can generate some fake data of the sine curve by creating a list of values, which is my t. So it just goes from 0 to 20 times pi, which is about 62 or so. And it just creates some data using this function up here and adds some random numbers to it again, just to make it more like experimental data. And so you can see it's got some kind of oscillation to it, but it's a bit messy, a bit noisy. This may be the sort of measurement you get if you're working, at least in my case, in a lab doing some physics, or even doing chemistry or biology, something like that. You may measure something in your experiment that looks like this. It has this sort of behavior. And usually when something that has this sort of behavior, we'd want to find out a few useful parameters, one of them being how high is this curve? So you see it's some amplitude from 0, some distance from 0, and how rapidly does it oscillate? And which is also the distance between the peaks. So to find those out, we want to fit that data. So this is when we're going to use this curve fit that I showed you before. So here, like I mentioned, you give it some, as the first argument, some function. In this case, the function is sine curve. That's the one I showed you just before. Then the x data is the t, it's the horizontal axis. The y data is what I've called fake data, which is the y-axis. And then this p0 is some initial guess. Now, you don't have to give an initial guess here. you can leave this blank, but it is useful to try and guess what you think the answer of your fitting will be before you fit it to help the computer do it more effectively. So the way we write these guess parameters is using a Python array like this, where you give it just the numbers you think are the answer for the arguments to your function. So up here you can see the arguments of my function are a, w, and phi. So I have to give guess values what I think a is, what I think w is, and what I think phi is. Now for a, it goes from 0 to about 2, so I guess 2. But the distance between this peak and this peak, well, it's not quite. It's probably, sorry, this peak and, yeah, this peak down here is about 10 or so from here to here. And this I have just guessed randomly. This is the phase. It's a little bit hard to guess this because it's just about an offset from the curve traveling left or right. So that's just a bit of a guess. And then feed that into this curve here. Oh, yes. Sorry.
I'm sorry, Dylan. Actually, it was kind of confused for me. Do we know that the graph of sine function like moving or moves
Right.
between interval 0 up to 1, but it goes up to 2? So it was kind of, maybe it's because you generated some fake values. That's why. I don't know.
Yeah. Okay. Yeah. Sorry. Sorry if I didn't make that clear. So yes, the sine normally goes from, yes, you're right, -1 to 1. But I have multiplied it by some number here. So I can make this number, by multiplying it by some number here, it increases the height of the function. So I can make this, make this 10, for example, and now you see it goes up to 10.
Okay.
So it's, yeah. So that, sorry if I didn't make that clear. Maybe I'll also show you what I mean by this phi value here as well. So by making that 0, the sine curve looks like this. It starts at 0 and then oscillates up and down. If I make it equal to probably that's the wrong number. Some number here, it just now starts at 1 and oscillates. So this phase on the sine just kind of moves the data left and right. It's as a visual representation. I think I recommend playing around with that if that's something that you want to get a feel for as well.
Thank you. Got it. Thank you.
Okay, so this curve fit now, if we've given it the function and our data and some guess of what we think the answer should be, and it returns two variables here, one which I've called popt and one which is called pcov. Popt here are the optimal parameters. So it's what SciPy has determined are the best parameters for this fit. And we can have a look at that by printing it down here. And we see that it's given us 2.01, 10, and 0.7. 2 is pretty basically equal to what we guessed. 10 is again basically equal, and 0.7 is actually basically this pi over 4. So that means our guess parameters were quite good. The other thing it's given us is pcov, which is this 3x3 matrix. I will talk about this in more detail later on, so I won't, just to not be confusing now. But this is very important for understanding how good our fit is. And looking at these parameters, it seems like it's a good fit, but of course we always want to check by plotting the data. And so what I've done is plotted the kind of my fake data here in blue, and then overlaid on the same plot the fitted function that we've just generated here, like this. This type of notation is something that you may not be familiar with. If I have some array of numbers, like p-opt here, and I input it into a function with the star here, it's just telling Python to input these numbers in order as arguments to the function. So it would be identical to writing this, which is more time consuming. So as a time saving technique, what we can do is just use this star p-opt, and it gives us the exact, this is the same answer. So as you can see, they're plotted directly over the top of each other. So it's exactly the same. So that's great. So that's one example of fitting a sine curve. Now, a sine curve, there's only so many ways you can fit a sine curve. What we can do is, you can try changing the frequency to make it so that it has twice as many oscillations. It starts to look a bit hard to see by eye. But what we can see is that the guess parameters here will be wrong. So I won't change these. So now this guess parameter is completely wrong. But if I now try and fit the data, it doesn't work anymore, because it tries the initial guess that I gave it, has absolutely no idea what to do with it, and it just gives us this curve, which you can see does not fit the data at all. But now if I change the guess to be 20, and then try again, you see now it understands and it goes, oh, okay, I can actually fit the data to this. So if the guess parameters are completely wrong, it can stop it from fitting. However, if they're only slightly wrong, so if I say 17 instead of 20 for the frequency of the sine curve, okay, that's a bad example. It also doesn't know how to fit it. So sometimes it can be sometimes it can be okay, but sometimes it doesn't know what to do. Yeah, this is a bad example of a curve to use to show that it doesn't matter. Sorry about that. But yeah, sometimes you can get the guess parameters quite wrong, and it won't have a problem. Well, what is going on here? Yeah, so sorry, I think my code accidentally ran all of it. Yeah, so here, okay, yeah, so we can see that if we get the guess parameters wrong, it doesn't fit very well. So it can be quite important to try and estimate what these parameters are for your fitting before you start trying to fit for more complicated functions. And you'll know very easily if it's wrong, because like I just demonstrated to you live, if I put in the wrong parameters, it doesn't work. The next thing I want to talk about is something a bit more complicated. So the Gaussian function that I mentioned in my intro slides there. This is a very common one for if you're dealing with statistical data. So wanting to find distributions of some quantity. So like I gave the example of the height of people, how tall people are from some population. But it's also, you'll find it in almost any situation where you're working with sampling of data, so any kind of survey or any kind, like if you're surveying people about something, asking questions, you're trying to determine, like I said, how dice rolling works. You're trying to count the number of, the average distance people drive to work each day from their house. These things you'll often find the Gaussian distribution, or the Gaussian function, or normal distribution. Another function that looks very similar is which is also used in some statistical cases, is called the Cauchy distribution, or a Lorentzian function. The reason I want to bring this up is because they look very similar, and it's just as a way to show that even very similar looking functions sometimes will be quite, you can sort of fit them to data, but that might still not be the best choice. So just as a first, I define my functions like I showed you with the sine function here. The Gaussian function looks something like this, where it uses the exponential function from NumPy. It has some x0, which is an offset from 0 on the x-axis, so you can move this Gaussian peak left and right, and a sigma, which is how wide the peak is, so it can be wider or narrower. Again, I've got these Wikipedia links here that have a lot more information about what these functions are like. The Lorentzian function is very similar in shape. It's a peak that looks very much like a Gaussian. It's just slightly different in some important ways. Again, it has some height, A, which I didn't mention for Gaussian. A is the height of this peak. It's got some width of the peak. In this case, is gamma, how wide it is, and an offset and some distance offset from 0. So it's very much sounds at first very much the same thing as the Gaussian function, but as you'll see, they look quite different. To demonstrate this, I'll create some fake data again using my functions, and plot them on a curve. So I've just created some fake Lorentzian data and added some noise to it by making some random numbers just to make the points jitter around. And I've done the same thing with the Gaussian and then plotted them on 2 separate plots. Now, it's hard to show them both on the screen at the same time, but as you see, the top one is the Lorentzian function and the bottom one is the Gaussian function, and they look pretty similar to each other. You have some kind of peak in the center that drops away rapidly before it reaches the edge. The only thing you may have noticed is that the Lorentzian is narrow and the Gaussian is wider, and also you may have noticed there's a slightly different shape to the peak region here, but it's kind of hard to see. So we can try and fit, just as a little demonstration, fit both of these sets of data with both functions and see which one fits the best. At first, we need to guess some parameters, as I just showed you. If you guess these wrong, it makes a very bad fit. So we'll just try and guess what we think these parameters should be for this Gaussian function. So let's just take the Gaussian function for now. So the first one we need is A, which is the height of the function, or height of the data, and it looks to be about 5. So we can just write in 5. The second argument of the function was this x0. How far off from the 0 position on x does the function sit? And well, the peak sits nicely above 0, so we can leave that at 0. The next thing was the width, the sigma on the bottom here. How wide is the function at kind of halfway up? This is a little bit harder to. The half width at halfway up, and it's about I guess 2.5 or 3 or so. It's not quite so important, the width on this one. And then the fourth one is this constant value, which just lifts the entire set of data up and down. It's a constant offset. But as you can see, it's at 0 at the edges, so we just leave it at 0. We can use this guess actually for both of the sets of data because they both have approximately the same height, approximately the same width, if you want to call it that, and they both go to 0 at the edges. So we can try using the same guess for both and just see how it works. So that's, again, using this curve fit function where we give it the function we want to fit. In this case, I've given it the Gaussian function. We've given the x data and the y data, where x is the horizontal axis, y again is this test or fake data that I've made in blue, and the p0 is the guess. I've done this for both the Gaussian and the Lorentzian function, and given it the exact same data, the exact same guess parameters, and you can see that it's managed to fit both of these curves to the data. So the red one here is the Gaussian, and the blue one here, the green one here is the Lorentzian. And I hopefully it's very clear that while they both look like they're a good fit, the green curve is significantly better than the red. So the red here we can see doesn't really work at the edges, and also on the curve up towards the peak here, it doesn't fit properly. It doesn't get the height of the data in this region correctly, and also at the peak here, it doesn't get the height correct. So this is just a a small thing we can notice when trying to fit this. If we do the same thing but with the second set of data, so if you remember I had 2 sets of data, you can see that the opposite case is true now. That the red curve, which is the Gaussian, fits very nicely the blue data here, especially in the region where it didn't work before, where the green, which is the Lorentzian, doesn't fit well at all. It's a very, very bad fit. And so in this case, by eye, we can have a look and really try and understand what is good and what is bad. But sometimes we don't want to just have a check by eye. I don't want to just look at my data and go, well, this one looks better than this one, because it can be a bit subjective. Sometimes it's purely it will come down to what I feel like looks better. And so for that, we can actually do this mathematically or numerically by using something called the root mean square deviation. It's a long name for something that is essentially telling us how far away is the curve, so say this green curve, from the data on average. It just measures the distance between the two and tells us some number at the end. It's sort of like, well, you can think of it as being equivalent to this r or r squared value that I mentioned earlier for the straight line, and that it tells you how good quality your fit is. Now, this is a little bit of a tricky one to calculate, but we can just type in this function straight away. So essentially what it is it's the square root of this big thing underneath, which is just the each data point, which is this x, minus the function or the fitted function at the same point squared, and you do that for every single point, and you add them all up, and then you just multiply that by 1 divided by the total number of points. So how that looks is like this. So we have the sum, as you can see here, the sum. So this just takes the data, which is test data 2, and does the subtraction of the Gaussian function data. So that's the red curve. And it does the blue points minus the red curve at every single data point, which gives it some array of small numbers, squares it, takes it to the power of 2, and then multiplies it by 1 divided by the number of points, which is this 1 over n. And that gives some number. In this case, it's a very small number. This e to the minus 7 means 10 to the power of minus 7. So it's a lot of 6 zeros after the decimal point. So 0.00000005. Very small number. We can do the exact same calculation for the Lorentzian function, and we get a number of 1.4. Now, the numbers immediately might not mean anything to you, but what we can tell by looking at these two is that essentially the distance between the fit of the Lorentzian is larger than that of the Gaussian by a lot. It's almost 10 million times further away. So the Lorentzian fit in this case is a bad fit compared to the Gaussian. Now, this, I think, is maybe a little bit tricky. So what I would suggest is perhaps in your own time after the lesson, if you want to understand more, try and do the exact same calculation, but for this data here that I've shown you, the test data 1. See if you can come up with a number for root mean square. I think it's a good task just to try and understand, because this is a little bit more complicated than anything else I've talked about so far. Okay. So I'll move on to the next part now about what I call fitting with weighted data. Now, in a normal experiment or data collection, all your data has some level of uncertainty. And so I've tried to show this earlier by having the data points kind of randomly placed around. But you often have some kind of measurement uncertainty. If you measure a distance with a ruler, you can say this is 10 centimeters long, but there's always a bit of uncertainty, especially if what you're measuring doesn't line up perfectly with the lines of the ruler. Also, and that also carries over to any type of measurement. You always have some kind of uncertainty in your measurement. Now, this is something that we care a lot about in terms of scientific data analysis, because we're always trying to make the most accurate measurements possible. And one of the ways that we can use SciPy to actually help us with this is by taking our measurement uncertainties that we have from making our measurements and put them into the curve fitting function and telling SciPy which data points are the most accurate and which data points are the least accurate. And that'll help it fit the data in a way that better represents the real sample. Now, this is, hopefully that makes sense, but I'll show you an example here to try and explain what I mean by this. So we have our test data from before that I showed you, this Gaussian function. And I'm going to now try and fit this by assuming each of the data points on the curve, so each of these blue points here, has an associated uncertainty. So while we think this number here might be 5.5, there'll be some, we're not entirely certain that that's the actual number. That's what we've measured, but it could be something else. And so the way I'm going to do that is by creating some uncertainties of the data. Because it's not real data, I have to make this myself. I'm going to do that by taking what is the essentially the standard deviation of the data from earlier. So the standard deviation, if you recall from what I mentioned earlier, is how much the data varies from its average or mean value. When I created this fake data up the top here, in the code here, I've used this slightly different random number generating function. I didn't talk about it before because it wasn't important, but now it is important. So this generates a random number with some standard deviation given by the scale. And so the standard deviation is just, if I generate 100 random numbers, what's the average deviation of these numbers from one another? Like, what's the size of the sample I'm randomly generating from? Again, if this is a little bit complicated, I'd suggest looking up some of the documentation for this function, or for looking at the normal distribution page that I showed earlier. But essentially, what I'm saying is that each of these data points has some uncertainty in the measurement that is given by these blue bars on the data point here. So the blue bars are error bars, and each of these data points has some uncertainty in that the value lies between kind of the peak of the blue bar and the bottom of the blue bar. So it's centered at this data point, but there is some range over which we think the data could, the true value could lie in. Now this happens all the time in our measurements, as I mentioned, like when you measure with a ruler, for example. You know a range of what your measurement will lie in, but you're not entirely sure that it's precise down to, you can never be truly precise with your measurement. And so what we can do is take these errors and put them into SciPy using this sigma argument here that I mentioned before, which gives it the errors of the data points, and then it will fit and it will treat the data points with the smaller errors as more important, because it thinks that well, these are much more accurate measurements, so they must be more likely to be true than these measurements. And so you can see that the fit down here is very good to these points because they have small error bars, and up here, not quite as good because they have large error bars. So ideally, by including this in here, we improve the quality of the fit, because it allows SciPy a little bit more freedom in how it changes the fitting parameters to get a better fit, because it's allowed to move within the range of these error bars now. We can check that. We can check that by looking at the result of this fit by looking at this thing here, which I haven't talked about, called the covariance matrix. I've included a link to the covariance matrix somewhere in this document. It's complicated to understand, so I won't describe the whole thing, but the important thing is that the diagonal parts of the covariance matrix, so if I look at the covariance, if you remember, I showed you this briefly earlier on, the covariance matrix is a large matrix of numbers. In this case, it's a 4x4 matrix. But the diagonal elements, so the numbers along the diagonal, so there's 3, this 8, this 1, and this one, the diagonal elements are the variances of the fitted parameters. Now the variance is the square of the standard deviation. So by taking the square root of the diagonal elements, we can get the standard deviations of all of our fit parameters. Now, by looking, the standard deviation, as I mentioned, is how much does the how much does your kind of data spread around the mean value, but also you can think of it as kind of how certain are we in our measured and our fitted value. So a smaller standard deviation means a more accurate measurement in this case. And so by looking at these standard deviations here, we can see that when I use the weighted fitting here, these standard deviation numbers are much smaller than when I do not use the weighted fitting from earlier. And so hopefully it's clear from this that when we are working with real data, understanding how accurate we've been in our measurements is really a useful way to get much more accurate fitting of the data. Yeah. Okay. Now, I'd like to move on to the next part, as I have a few things to get through. I'd like to get through before we finish, but I'll give some time for questions at the end as well. So please don't worry if you still have some questions. Another useful tool is in some data. Sometimes we want to figure out where the peak of the data is. So you have some series of, I don't know, some measurements, and you want to find out where a particular peak of the data is. So if I have, for example, I'm pulling this data here from online, which is the monthly milk production in pounds, and it just shows, the data shows how milk, the production of milk per month, and it shows some kind of trend. And if we were wanting to, if we were working for this company that produces the milk, and we wanted to know which month do we have the greatest milk production, one way you could do that is look by eye and see where do I find the peak of the data. What's the highest value? You know, which months give the highest value? But that's time consuming, and depending on how complicated your data gets, can be unreasonably time consuming. And so that's where there's this useful function in SciPy. It's under now the signal package, which is called find peaks. And so what that will do is it'll look at the data and it will find the peaks of the data and return them to you. And you can then check and see if that actually makes sense. So the first thing I want to do is just show you the data. So this is the data of monthly milk production, where the x-axis in this case is a number of months, and the y-axis is just milk production in pounds. And you can see that it has a series of peaks. And let's say we want to know, what months do these peaks correspond to? Well, that's where we use the SciPy. And so, like I mentioned, it's the SciPy signal package, and we can import this find peaks function. Just in case, when importing things from in Python packages, you don't have to do it exactly the way that I've written it here. You could also just import SciPy.signal as something else, like sig, for example. And then anytime I wanted to use the find peaks function, I can just go sig.find peaks, for example. There's no one way to import stuff into Python. I just wanted to make a note of that, just in case you were wondering. So this here is the find peaks function. This is a very simple one to use. You just give it the data. In this case, this is why I've just called it time series. And it returns you something. I'll show you what it returns normally. That looks like this. It's just a big array of numbers, but it's got some other information there that we don't want. We don't want that. So that's why here I take the 0. This is the first element of this returned set of data, because I only want this array, which is the location of the peaks. And so you can see now this has just taken the peak locations. So now each of these numbers corresponds to a position in this data where a peak occurs. It's important to note that these are these numbers are the index of the array and not the actual values of the horizontal data. So 4 means the 5th element of the array, because it's Python indexing, so we start from 0. So 4, you can see, if we can roughly see, this is the 0th element, or the first one, 0, 1, 2, 3, 4, and it's the peak. You could then count your way along and see that these other numbers also correspond to peaks as well. As an easier way, though, rather than just counting, is to plot the data. And I'm just going to put little crosses in red over the top of the peaks. So by plotting the data as normal, we can then index the array using these peak locations to only plot the data at those points, like this. And we see something like this. Now, you can see that it has found all of the peaks up here, which is very nice, but it's also found all of these little peaks down here. And this is not very useful to us because these peaks are not what we care about. These are just kind of random spikes in the data. What we're really caring about right now are the big, tall peaks up here. And so there are a lot of ways that we can use this find peaks function to isolate the data that we care about. One of them, so there's a few parameters such as the threshold, which tells it the minimum height difference between neighboring data points, the distance between peaks, which is how far apart they are horizontally, the height of the peaks, which says how high on the y-axis are they. And we can change these numbers to try and get a better fit. So as an example for threshold, that's the one I mentioned. It's the distance between neighboring points. So if this peak here is to be considered a true peak, the points on either side must be more than 30 below itself. And it's you see that it can eliminate some of the peaks, but it's also eliminated a lot of peaks that we want. And you can see why when you start to look at the ones that's ignored. I've set the threshold as 30, but say for this peak, this point and the next point to it, which you might be able to see here, are definitely, they're very close together. And so that's why it's excluded that point. This can be useful if your data has really large spikes, if you really want to eliminate just small noise. But if you have data that's a little bit more in the in-between, threshold might not be very useful. So again, I've just mentioned here, if you want to, you can try adjusting the threshold value yourself and just kind of get a feeling for how that works. The next one is, no, this should be, sorry, this is border. That is a mistake. That should say height. The height can be used to find peaks that are of a certain height or within a range of heights. So I can say I only care about peaks that are between 700 and 800. So that's anything between here and here on the graph. And you'll see that I get all of the peaks that's found lie between the 700 to 800 range. Now that's seeming a little bit more useful than the threshold, but you can see that it still doesn't really find all of the main peaks that I want. But this this height boundary here, though, this height limit that I've set, these don't have to be numbers. They can be any kind of mathematical description that we like. So I can make a straight line, for example. Now this is just a straight line that I have made up that just runs from about 650 from about here up to about 1,000 up here. And I've just said anything between these two green lines is allowed to be a peak. Anything outside of those lines is not. And as you can see, it's basically straight away found all of the peaks in here. It's only missing this last one just because of my choice of boundary. And so this has now told us all of the peaks that we care about immediately from this. And so if I was now trying to report to my company, I now know what all of our best months are, the best time of year for producing milk. I now have that data ready to turn over. Another feature that I did mention is this distance. This distance, as I said, was the distance horizontally between peaks. You can also use this one as a way of removing any kind of, if you have very noisy data, you have a lot of spikes. If you know how far apart your peaks should be, you can use this distance. And so this data is periodic. It should be monthly or yearly. So it's in months. So you should say each peak should be, well, would be 12 months apart. So if I say all my peaks are 12 apart, you can see it just automatically only finds the main peaks, because all of these other ones are just a bit of noise. There are plenty more applications for peak finding than just this sort of data. This is a function that I use all the time for finding peaks in all sorts of different data types. But have a play around with the code and see if you can just kind of get an understanding of how it works. So I'm just looking at the time. I don't think I'll get through everything I have planned for today, but that's okay. I won't rush through it. I'll make sure to cover everything, and I just might have to leave some stuff till next time. The next thing is route finding that's useful. So by route finding, what I mean is where does the data cross over the 0 point of the vertical axis? So that is very useful when you're trying to trace data back to its starting point, or if you want to Let me think of an example. Yeah, maybe I'll just show you. I'll show you. For that, there's a function. This is from the Pi astronomy package that I mentioned, because this is a function that astronomers use all the time, but we can make use of it for non-astronomy tasks. For this one, it doesn't come pre-installed with Python, so you will have to use this, install it using pip, just like this, and it should install the package for you. Great. So if you just also if you search on Google Pi astronomy, just written like this, you'll find all of the notation on it. If there's anything in there that you're of interest to you as well. It's like I said, it's mostly focused for astronomers, but there are some useful things in there. Now the root finding function in Pi astronomy is called 0x1d, which just means 0 crossing in 1 dimension, and we import it like this. Now, as an example of what I mean, let's say we have some data that looks like this. Doesn't matter what we're trying to measure here, but it's some curve which looks kind of periodic and goes from some large negative number to some large positive number. And at some point along the curve, we can see it crosses over 0. Now, let's say we really wanted to figure out where this point crosses 0 is. This is actually quite a hard thing to do. Without this nice function. It can be very challenging to figure out where it crosses 0. Exactly. This is a tangent graph. Exactly. I've used it just because it's a great example of the sort of data I'm talking about. Now, for this, we use the 0, like I said, 0x1d. We give it the x data, which is the horizontal, the test data in this case, which is the vertical. And I've just said I want the indices. This just tells it to give me the array positions, not just the actual numbers of the crossing, just because it's a bit more useful. And we can see that it gives us the excuse me, the positions where it crosses over 0, the values, sorry, where it crosses over 0, but also the positions in the array where it crosses over 0. Now the value is 1.7 minus 1.7. Well, that's maybe about here. That lines up nicely. Minus 1.5. That's probably about here or so. On this vertical line, it's a bit hard to tell. 1.3 is up here somewhere. 1.5 again, this vertical line here. So you can see that it's found the points nicely. But we can check that, of course, by indexing the data. So that's why I wanted these indices, because this just tells us where in the array does it cross 0. And we can see that it crosses this, that it crosses the 0 nicely. So if I just look at the crossings position, which is what I call the result here, it's picked out the crossings nicely. This is something that I use all the time, at least in terms of physics application. I'm not sure of an application maybe in other areas of research, but I'm sure it's something that I would say keep in mind, because there are many cases where you want to figure out where a function crosses over 0. Okay, the last 1 or 2 things I will cover for today is some filtering of data. So as I showed earlier, you have some noisy data. It's got some uncertainty on your measurements. You want to try and fit it, or you want to try and understand what the data is showing you. It can be really hard if the data is very, very noisy. This can happen if you have interference with your signal. It can happen if you have a bad measuring device. It can happen if you're measuring multiple things at once. So say if you have a microphone, right, you're trying to record someone speaking, but you have a very high-pitched sound in the background, that'll, in your data, you'll have some kind of interference. You'll have noise in your measurement. And there are a lot of ways to deal with this, but one of the ways that I'd like to talk about is using these low-pass, or in some cases high-pass filters, to try and filter out unwanted noise. The SciPy package, again, is what we'll be using for this. Again, the signal package. So specifically these three parts of it here. So butter is a type of filter called a Butterworth filter. I've got a Wikipedia link here if you want to read more about it. L filter, which is just another filter function, and freq_z, which just generates frequencies for the filter. So you'll get an understanding of what these do as I work through this. So let's create some data. Again, I'm going to generate my own data here. I have some length of time, say 5 seconds, that I've recorded some data over. I sample the data at some sampling frequency. It's how many measurements do I take, or how often do I take a measurement? And then my total number of data points is just how long I'm sampling times how many samples per second. And so if I sample 30 times a second for 5 seconds, then, well, I get 150 samples total. And then I'm just going to generate the data by adding together some various sine and cosine curves together, just to make something that looks a little bit messy like this. And so you can see, from by eye, I can see there's a kind of, an underlying sine curve here, and that's what I want to measure, this main sine curve. But the data has all of this noise on it. It's all spiky, and it makes it very hard to see. Sometimes when you can also think of this as an audio signal. If I wanted to have a single sound note, and I had all of this noise on it, it would sound all horrible and have different frequencies mixed in there. So what we can do is try and filter out this higher frequency noise and try and pick out the lower frequency stuff. And so that's what's using this thing called a Butterworth filter. The exact mathematics of the filter is not so important for this. The main thing to understand is that when we have a filter, we have some kind of cutoff frequency where we say, above this frequency, I don't want anything at that frequency anymore. Has a sampling rate, which is the same as our sampling rate of our signal before, and an order, which is just kind of determines the order of the filter. Again, that's a mathematical thing. For here, we just use 5. And then we just produce a filter like this. And we can show by what the filter looks like by just kind of creating it here. So if I just say, well, I've said here order is 6, but and the cutoff I'm going to say is 3.6. That's just some 3.6 hertz. And I've chosen that number just because it's small enough that it won't affect large enough that it won't affect the data we're trying to find, but small enough that it should eliminate the noise, and produce some kind of filter. We can see what the filter looks like by plotting what the filter does to signals of various frequencies. With this bit of code here, most of this code is just generating the plot. What we can see is that for everything below the cutoff, which was 3.667, it almost leaves it unchanged. So for most of the low frequencies, they transmit completely with 1. But once you go past the cutoff, they very quickly removes anything with higher frequency than that. So you can see up here, it's now at 0. So if you apply this filter to anything, say 8 hertz and above, it'll eliminate everything at that frequency. This is very much the same thing you'll use in music production as well. So if you're making music, or you'll often use low pass and high pass filters in exactly the same way to filter through your audio. We can then apply the filter to the data to see what it does by creating the filter and just multiplying it, applying the filter to our data here, which was this other function up here. It just takes the filter that we've generated and applies it to the data using this lFilter function from SciPy. But you can see straight away that what it does is it takes this blue data and filters it out to give us this green signal. The green signal here is the filtered data. You've probably noticed that there's a delay, though, between the green and the blue. There's an offset in time. This delay is just as a side effect of the filtering, where you will always get a phase shift or a time delay of your filtered signal. And again, if you're familiar with audio engineering or with music, you'll know that when you play your instruments or something through a low-pass filter, you'll also get a delay in your output audio. This is the exact same thing that's going on here. If you're familiar with electronics, or you've done some electrical engineering or built some simple electronic circuits, this is another thing you'll notice if you're dealing with an analog circuit, is you'll see a delay in your analog signal when you use a low-pass filter or a high-pass filter. But the underlying information is exactly what we want. Now, this sort of filter, there are other types of filters, of course. There's a high-pass filter, which lets high frequencies through, cuts out low frequencies. There's band pass filters, which lets frequencies through in a small range. They're all done exactly the same way as I've done here. So have a go if you want and see if you can apply some different filters to this data. So looking at the time, I wonder if it's better actually. This will be a bit more complicated. So looking at the time, I wonder if it's better if I finish up here and allow if there's any questions about anything I've talked about, and then I'll keep the next section for next time because it'll take me probably longer than 15 minutes to go through the next section.
Thank you very much, Dr. Delan. It was super great presentation from you. Right now, if there is any question from participants, please feel free to ask. I think we have no any question in chat box yet. Yeah, Abida, Danish, please.
Actually, the topic of threshold somehow left me a bit confused.
Okay. You mean for the peak finding up here?
Yes, it was
okay.
above.
Yeah.
Above.
Okay. This
Yes.
part here. Okay. Yeah. This is a little bit of a tricky one. So, threshold means what difference in height is there between a peak and the data point immediately next to it. So in this case, what it says is that in order for it to be considered a peak, the nearest data point, so if you go 1 point to the left and 1 point to the right, both of those need to be more than the threshold lower to be considered a peak. So as you can see here, the 1 point to the right of this point is all the way down here. It's about 150 away, maybe 200 away. This point over here is maybe 100 away down. So it says, okay, this is allowed to be a peak because those numbers are bigger than the threshold of 30. For the points like this one to the left might be more than 30 down, but to the right, it's only about 10. And so in that case, it says, well, that's not within the threshold. This is probably, of all of the ways you can use the peak finding, I would say is the least useful one. The height and the distance are much more useful. Threshold is, there are situations where it's useful, but I have not really come across many. Hopefully that makes sense.
Okay, thank you. And one more, I can say one more random question. For today's assignment, I wanted to upload like my data frame or data set through, in Google Colab through my Google Drive. And I used I mean the viewer method, but it doesn't work. Like it says that the directory does not exist or something like such kind of things.
Okay.
Content, /content /drive, and I don't know which part did you.
Okay.
list over.
Yeah, that's okay. So in the Google Drive, so for me, this is what my Google Drive folder looks like on the left side here. So usually, yeah, this drive mount should work okay. If you do this part and this part here, the big part, I guess, that makes it work for me is using the Python function to change directory afterwards to make sure that the working directory of the script is set to where your data is saved. So in my case, it's this folder here, this advanced data analysis lesson 1. And so as long as I set the change directory to this, then it should have access to all my data. Is that the problem you were having, or is it more to do with the drive mounting that doesn't work?
I think, yeah, it was some issues. Something was wrong with the drive mounting. So
Okay.
I had to upload the data set through Jupyter Notebook, and yeah.
Okay.
for
Okay.
it to be fine. Yeah.
Okay. Yeah, I'm not sure about that issue, unfortunately, without seeing the exact kind of situation where it's not working. But yeah, I guess you're welcome to email us and ask us if you still have problems with that. But if you manage to get it to work through Jupyter, then I think hopefully that works well.
By the way, I will give it a try. I hope to be able to manage it.
Okay.
Samira Amiri, please.
Can you hear me?
Yes.
Yeah.
Okay. My question is about Sigma. Can you give me a little more information about Sigma? Why is Sigma equal to none?
Sigma. So for Sigma, you mean for which segment are you referring to here? Sigma for. Sorry, could you please tell me which segment do you mean?
You explain about. I'm not sure where is that, but you told that Sigma is equal to 9. But I really don't know about Sigma. What's Sigma?
Okay. Was it down? Was it this part here, maybe? So yeah, I'm sorry about that. I'm sorry that I was confusing. The Sigma can often mean a few different things. So I'm just going to, I hope I'm talking about the right part here. So one of the Sigmas that we used was this this uncertainty in the data. Is this
Right
what you're
here.
meaning? Okay. Right. So what I've done is created some data. Let me go up to the top here. So I've created some data. Can I hide this figure? Which is the red curve shown here, and I've added some jitter, some noise or uncertainty to the data. And the amount of noise that I've added is this based on this number here called scale. And what that does is it just says, when I make a random number, what is the range that these random numbers can fall between. So it's just in that case, this is the standard deviation of the random number generator. So that means that each of these data points, the jitter they have is about 0.08 in this case. So I've then assumed that this number is my uncertainty in my measurement, so that when I do the fitting down here using sigma, which is the uncertainty in these data points, I have just used 0.08 because it was the same standard deviation as before. Each of these data points has some uncertainty, which is about 0.08 times itself. I don't know if that makes sense. Sorry if that was a bit confusing. It's just the number is just purely, it's chosen purely as a number that just because there's no reason for it being 0.08. It's just because that's what I used earlier to generate the data. But it's just the standard deviation of the random numbers is 0.08. That's what that means. So maybe as a, I don't know if this helps explain it, but as a
Yeah, thank you. I have
Okay.
got my question. Thank you so much.
Okay.